let's continue from where we left off. Anybody have any questions right now or any comments, concerns at this present time? No? Okay, this is where we left off last time. Now, this particular chapter, what what this chapter is all about is the electrons. The previous chapter, we talked about the model of the atom and how the model came up and say to determine that we had a nucleus, and in the nucleus was a proton, and then the neutrons were in the nucleus, and then the electrons were kind of like haphazardly just placed somewhere around the atom. Well, later on, more data, more information came into play, and it was determined that electrons actually occupy specific energy levels. Okay? And that's what this chapter is all about. Now, we're going to start utilizing what is called the electron configuration. And that's just basically telling us where the electrons are for the atoms. So on this particular page here, you can see, well, let me back up for a second. There are 7 energy levels, okay, which correspond to the 7 periods of the periodic table, 1 through 7. And within these energy levels, there are sublevels, otherwise called as orbits or orbitals, okay? There are 4 types of orbitals. There's the S, like in Sam. There's the P, there's the D, and then there are the F orbits, okay? Now, there's only one type of S orbit, just one S. The P's, there's 3. There's 3 P orbits, okay? And the D's, there's 5 of them. And the F, there are 7 of them. Now, each orbit can handle 2 electrons. So the S orbits can handle at the maximum 2 electrons. The P orbits, because there's 3 of them, can handle a total of 6 electrons. And then the D, having 5 of them, can handle a total of 10 electrons. And then finally, the F orbits, with there being 7 of them, can handle a total of 14 electrons. Okay, now, if you look at the diagram here on the right side, when we start writing the electron configuration for whatever element, you can see that starting with, let me get my draw unit here, starting with actually right here, hydrogen. Hydrogen only has 1 electron, and it's in the first period, which means that 1 electron exists in the first energy level, which is denoted by the 1 coefficient. And it only has 1 electron, which is in the S orbit, so hence we write it 1s superscript 1. If we shoot across to helium on the other side of the periodic table right there, helium has 2 electrons, okay? And also helium is in the first energy level, excuse me. Therefore, that electron, those 2 electrons, its electron configuration would be 1s2, okay? And this particular table really helps you along as you go through all the periods. You start adding the electrons sequentially as you go across the periodic table. If we shoot across right here, okay, that element is in the second period, and it has a total of 3 electrons. That means that the 1s2 is full, and then the one that's left over is in the next energy level, 2s1. And we continue across the periodic table. Next one, again, that electron is full. So we got 2s2, etc. As we shoot across the periodic table in this direction to boron, remember that I said when we talk about the elements denoted by 3A all the way to 8A, think of those as the P. then we start filling up the p orbits. Okay, so we go across the periodic table to 2p1, all the way across the neon where the electrons are 2p6. All right, so and so forth. So sequentially, so this table kind of really shows you how things are filled up. So if we take look at the one on the left, that's phosphorus. Phosphorus is right here. Okay, let me clear that up for a second and try something else. Phosphorus is right here. Okay. All right, so we start writing the electron configuration for phosphorus. It has a total of 8, 10, 15 electrons. Okay, so as we shoot across here, we start filling them up. 1 is 2. Okay, that takes care of 2 electrons. And then we go to the next energy level, 2s2. That takes care of 2 more electrons. And then we go all the way across to 2p6. Phosphorus electrons then occupy the 2p6. And then we shoot back to the third energy level because that's where phosphorus is at. And we fill up the first 2 electrons. Okay, so 3p(s)2. And then finally, 3p3. Okay. Now, the third energy level is what we call the outermost energy level, the outermost level that the electrons exist. Phosphorus has 5 valence electrons. 5 of them. The valence electrons are their outermost shell. That corresponds, if we look at the other periodic table, you will find that is denoted by the Roman numeral VA. So everybody, all the elements in the VA group have 5 valence electrons. They're going to be in different levels. The one below phosphorus, it would be at 4s2, 4p3, okay? So on down the road because they're bigger elements. And this is kind of introduce you to another trend here because as we go down the periodic table, guess what? The atoms get bigger. Okay, we're adding, as we go down the periodic table, the atoms are larger number. They have a larger atomic number, more protons, more electrons. Okay, so down the periodic table, the general trend is that the atoms get larger in size. Now, those valence electrons are extremely important. Why? Because that is where all the action happens. That is where all the chemical reactions occur. The core electrons, those are the inner electrons. These denote, and for phosphorus denoted by 1s2, 2s2, 2p6, they're full. All the orbits are full. So nothing's going to happen there chemically. Everything is going to happen out here. Okay? At the outer, the valence electrons. And we can always use the periodic table to, one, tell us how many valence electrons they have, because depending on the group that they're in, tells us how many valence electrons. Also, by finding it on the periodic table, we can determine and calculate or write out the electron configuration, or alternatively, we can use that table right here to help us to sequentially write the electron configuration. I prefer to use the periodic table because I don't have to sit here and memorize the sequence, because the periodic table by default just tells us everything. Let's get rid of some of this drawings. Okay, so the coefficient, the 1, 2, 3, and 4, just tells us what energy level it is. The superscript tells us how many electrons for that orbit and that energy level. Now we can look at the periodic table and look at chlorine. Let me pull that up. Chlorine, beryllium, and aluminum. Okay, let me pull up the periodic table. We use the periodic table. We don't have to memorize anything about it, just we have to find it on the periodic table. Let's look at chlorine. Chlorine is number 17, okay? It is in group 7. Now, first question would be, can anybody tell me how many total electrons does chlorine have? This is chlorine right here. Anybody want to tell me how many electrons does chlorine have? Just based on the periodic table and where it's at. Can anybody tell me that? You don't have to guess. It's right there. Okay. How many protons does chlorine have? Okay. Lua, you got 17. Exactly. That's how many protons it has. Also, how many electrons it has. Now, there's 17 electrons in chlorine. Of those 17, how many are the valence electrons in the outermost shell? Okay. What? 7, exactly. It is in group 7. Now, third question. There's 17 electrons. Of those 17, 7 of them are the outermost shell. What energy level is the outermost shell for chlorine? What energy level are those 7 electrons? Okay. What period is chlorine in? Meaning, remember we start at 1, 2, 3, 4, 5, 6, 7. Exactly. So those valence electrons are on the 3rd period. Okay. And 2 of them are 3s2. Okay. And the ones are in 3p6. Excuse me, 3p5. Okay. So let me write it down here. Let me do a new share. If I needed to write the electron configuration for chlorine, okay, we know that chlorine has 17 electrons. Okay. Plus we know that it is in the 3rd period. Those are the names of the horizontal I'm trying to the 3rd energy level. Okay. That means that 1s2 is full. I don't have superscript, so I have to use that. And then that takes care of 2 electrons, so we have 15 electrons to do. And then we go to the next energy level, 2s. 2 is full. We go all the way across the periodic table. That means that p electron orbits get full. So there's 6. So we got a total so far of 6, 8, 10 electrons taken care of. Okay. We know that chlorine's in the 3rd period, so we're going from left to right. So it's 3s2 gets full. 2. And then we're shooting across into the P elements, and we just count the columns, and it's 3p5. Okay, we should have right there, we should have a total of 17 electrons. These are the valence electrons right there, 7 of them, which corresponds to it being in group 7. Okay, all right, go back to where we were. Okay, so here's the electron configuration for chlorine. 1s2, 2s2, 2p6, 3s2, and 3p5. Okay. The valence electrons on the third energy level, there's 7 of them. Beryllium, okay, has 2 valence electrons. It's in group 2. Okay. So there's a total of 4 electrons for beryllium. Of those 4, 2 of them are the valence electrons. So its electron configuration is 1s2, 2s2. Aluminum, okay, has 3 valence electrons. It's in group 3a. Those 3 valence electrons are in the third energy level. So we go from left to right, fill up the s orbits first, and then we go across into the p's. And there's only 1, so aluminum is in group 3, so it's 3p1. The valence electrons, the 3 of them are in the third energy level. 2 of them are in the s orbit, and 1 of them are in the p orbit. Okay. All right. So we can use the Roman numerals on top of the periodic table. And this is only true for the A series, okay? If we look at the periodic table, it goes from 1A across to 8A. That group number represents how many valence electrons are associated with that particular element. Let me go back here. Okay, so if we look at the 1A, which is the first column of the periodic table, okay, all of them have different number of total electrons. What they all share is, the number of valence electrons. So everybody in here, in this group, though they're different elements, okay, sodium, for example, number 11 has a total of 11 electrons, but one of them is in the outermost shell, okay? Group 2, all these elements share 2 valence electrons. We shoot across to group 3, all these elements share 3 valence electrons, and etc. as we go across the periodic table. Now, the only exception is down here with the noble gases. Starting with neon, they have 8 down. Helium only has 2. It doesn't have 8 because there's only 2 electrons total for it. So its magic number is 2. But the drive here for all elements is to be like the noble gases of group 3 because they're so inert, and they're striving to pick up 1 electron to give you 8, or to get rid of electrons to give you 8 in the next outermost shell. And we're going to learn with time that everybody in group 1A and group 2A, they prefer to lose those electrons. Okay, we did chlorine. Everybody here in this group 7A has 7 electrons. Now ask yourself a question. I got 7 electrons. Would it be easier from an energy perspective to get rid of 7 or to pick up 1? Obviously to pick up 1. Why? Because I get that magic 8. So we're going to learn that all these nonmetals, as the closer they are to the noble gases, the more affinity they have to gain electrons. And when they gain electrons, they become overall negative charge. The metals, and you might want to put this in long-term memory, all the metals, they prefer to lose electrons, okay? And they end up with a positive charge because they lost electronegative charge, okay? They become a net positive. All right, let's go back here. Okay, so that's the number of valence electrons. Of course, helium, it doesn't have 8, it has 2. It just has, that's all it is. It has a total of 2 electrons. Question is here is how many valence electrons strontium has? Well, we got to find it. After we find it, we determine what group it's in, and it will find that strontium has 2 valence electrons. It's in group 2A. Bromine, like chlorine, okay, is in group 7, so it has 7 electrons. Argon, which is in group 8, is one of the noble gases, has 8 electrons. Silicon is in group 4. Silicon has 4 valence electrons. And then sulfur, okay, sulfur is in group 6, so it has 6 valence electrons. You know, 6 valence electrons. All right. So question is, why do atoms want to make compounds? And why do they bond? Okay. Well, just like I was explaining here a minute ago, the driving force for chemical reactions is to make stable species, or whatever they may be. And what happens is one of them may lose an electron while the other one gains an electron, because they tend to be in a more stable state by either losing or gaining electrons. The ultimate goal is to have their outermost shell full with 8 electrons. They're trying to obtain what's called the octet rule to obtain the 8. Helium is the only exception. It's a duet rule for helium, okay? Now, when atoms either gain or lose electrons, they become what we call ions, I-O-N, okay? That's what you're drinking. You know, when you are drinking electrolytes in some drink, and you say you need iron or you need salt, you need sodium, you're not drinking or ingesting the elements. You are ingesting the ions. These are the elements that either gain or lost electrons. Sodium chloride. Sodium, table salt, it's in group 1, okay? It loses 1 electron. And by losing 1 electron, it becomes a positive charge. Chlorine, remember, it's in group 7. It wants to pick up 1 more electron, okay? And by picking up an electron, it has a negative charge, so it forms sodium chloride. You have the chloride ion and the sodium ion, okay? For example, here's the electron configuration for sodium, okay? Sodium has 11 electrons. And if we do the electron configuration for sodium, it is 1s2, 2s2, 2p6, and then the valence electron is in the 3rd energy level, 3s1. Okay, it's in group 1. Point number 1, sodium is a metal. And like I stated, put this in long term, second time I said this, so it must be important. All metals want to lose electrons. So it's going to lose that electron in the outermost shell, 3s1. And when it does that, now, guess what? That shell is empty now. And the valence shell is the next one in, which is full, 2s2, 2p6. Now, it has, think about this for a moment. Sodium metal, the element, has 11 protons and 11 electrons. So in other words, it has 11 positives and 11 negatives. The net charge is 0. When it loses that 1 electron, it didn't lose a proton. it lost an electron. Remember, if it lost a proton, it's no longer sodium because the proton defines the element. And so now it has still has 11 protons, but now it has 10 electrons or 10 negative charges. What is the net? I got 11 positives and 10 negatives. What do I have left over? 1 positive. So now it formed a positive ion. Okay, and we denote that by the positive charge, the superscript on sodium. Right here. Okay, it's positive now because that's the ion. That is what you're ingesting. You're not ingesting the sodium element. Thank God, because the sodium element is very reactive, very hazardous. Okay, so the driving force is now to have a new valence shell. By losing this outermost shell, losing that electron, it shrank. Okay, so the ion is smaller in diameter than the element. Okay, and so now the new outermost shell is full now. It has 8 electrons. 2 of them are in the S, 6 of them are in the P. So that's the driving force for the metal. All right, now let's take a look at sulfur. Okay, sulfur is in group 6. Okay, so its electron configuration is 1s2, 2s2, 2p6, and then being in the third period, in the third energy level, those 6 electrons, 2 of them are in the 2s2, and the other 4 are in the 3p4. Okay, total 6 electrons. Now, ask yourself the question, energy-wise, is it easier to get rid of 6 or pick up 2? Well, in this case, it's much easier to pick up 2 electrons. Okay. Point number 1, I said earlier with sodium, it's a metal. All metals want to lose electrons. Okay. Point number 2, put this in long-term memory. Non-metals want to gain electrons. Sulfur is a non-metal, and therefore it wants to gain electrons. Specifically, it's going to gain 2 electrons. Okay, why? Because when in doing that, now the outermost shell is full with 8 electrons. Those 2 electrons they picked up, it stuck them right there in the 4p4. They had room for 2 more. So now sulfur has 16 protons and 16 electrons, the element. And by picking up 2 electrons now, it still has 16 protons, but now has 18 electrons, 18 negative charges. So 16 positive charges cancels out 16 negative charges, but there's 2 extra negatives. So the net charge that sulfur has is a -2. And guess what? Non-metals, when they become ions, we change the name. We talked about chlorine before, and by picking up an electron, it became chloride. Okay, so chlorine, INE, is the element. When it becomes an ion, we change the name to IDE. So sulfur now becomes sulfide. And that's the difference. The sodium doesn't change. The positive charge, it's still sodium. It's either sodium element or sodium ion. It is the non-metal that we change names for. Okay. Let me clear this up. All right, so the electron configurations for these ions. And why are they ions? Because they have a plus charge or a negative charge. Okay. And so here, potassium has a +1 charge. So it lost 1 electron. Nitrogen picked up 3 electrons. Now it becomes nitride, its name. Magnesium with a +2, now it becomes a magnesium ion. It lost 2 electrons. Okay, and then to write the electron configuration is the same. However, the difference is that potassium, the element, would have had 4s1. Okay, and it lost that electron. So now, by losing an electron, it has a positive charge, and the next shell in, which is the third energy level, is full. It looks like, from the electron configuration, like argon. That's a driving force. Nitrogen normally is 2s2, 2p3 when it's the element. When it picks up 3 electrons, those 3 electrons go into the p orbits, fill it up, the octet is full, and guess what? Its electron configuration is just like neon, the driving force again. Magnesium, same thing. Magnesium, normally its electron configuration is 1s2, 2s2, 2p6, and then 3s2, s2 valence electrons. When it lost those 2, it becomes the ion, magnesium plus 2. And now its electron configuration is like the noble gas neon. So by becoming ions, either positive or negative, they have an electron configuration like ions. Now, it's important, I didn't say that magnesium ion became neon, right? All I said was the electron configuration is like neon. There's a name for that. It's called isoelectronic. Okay, we'll show up here in a second. In order for magnesium to become neon, it would have to lose some protons, and we're not losing protons here. We can lose neutrons and electrons all day, but the moment we lose a proton, we change the element, okay? Because the proton defines the element. Okay, so when these elements become ions, you know, depending on what group they're in, if they're metals, they're gonna lose an electron. So all the group 1 elements, by losing an electron, become a +1 charge, okay? The group 2, by losing 2 electrons, okay, they become a +2 charge, okay? In group 3, they have 3 valence electrons. They will become a +3 charge, okay? So the group also tells you how many electrons are going to be lost and what kind of charge they're going to have. Group 7, they're closer to the noble gases on the periodic table. Okay, it's much, from an energy perspective, it's much easier energy-wise to gain electrons than to lose those 7. And so the elements in group 7, we're going to pick up 1 electron to give a mate. So they're going to have a net negative charge. The group 6, they're going to pick 2 electrons, have a -2 charge. Oxygen, for example, is in group 6. When it picks up 2 electrons, it becomes O -2. Its name, by the way, gets changed from oxygen to oxide. Okay, chlorine, when it gains an electron, changes its name from chlorine to chloride. Okay, so nonmetals want to gain electrons and become negative. The other name that you hear is anions. An anion, denoted here, is an element that gain an electron. Those are called anions. So group 7 has a -1, group 6 has a -2, and group 5 has a -3 charge. Okay. Metals, as I stated, once you identify, remember that periodic, that slide that we had they demonstrated who are the metals. All metals want to lose electrons. All non-metals want to gain electrons. Okay, and they become, the negative charge are called anions. The positive charge are called cations. Okay, so we have anions and cations. Trouble here. Give me 1 second. Okay. Anions and cations. Well, what about group 4? Well, here's the scenario. Group 4 has 4 valence electrons. They're like on the fence. Depending on the conditions, they can lose those 4 or they can gain those 4. Okay, and of course, you'll be told one way or the other, and it varies. There's no no set way to tell you they're going to gain or lose, but you'll be told if they lost or gained. That means that that's your reference point. So all the groups less than 4 will lose electrons. All the groups greater than 4 will gain electrons. All right, with the exception of 8. Remember, 8 are noble gases. They're not going to do anything. So from 5 to 7, they gain electrons. From 1 to 3, they lose electrons. Okay, it's because group 4 can, like I said, they can lose all 4, they can pick up 4. It varies. It depends on the conditions. And group 8, obviously, they're the noble gases. They're not going to do anything. So here are the charges across the periodic table. Okay, for the Roman numeral 1 to Roman numeral 7. Well, in this case, 8. There's nothing happens to the group 8 elements. Okay, so lithium, they're asking you here, what charge ion would they have? Well, first thing to do, as you look through the list, identify all the metals. Lithium's a metal. Magnesium's a metal. Okay, aluminum is a metal. So those guys are gonna lose electrons. Sulfur, bromine, and nitrogen, based on their position in the periodic table, are nonmetals. Okay, so those guys are going to gain electrons. Now, once you determine that, find them on the periodic table and what group they are. Lithium's in group 1, magnesium's in group 2, aluminum is in group 3. So those guys are going to have a positive charge. Lithium being in group 1 will have a positive 1. Magnesium being in group 2, when it becomes an ion, will have a positive 2. Sulfur is in group 6, and it's a nonmetal. So it's going to pick up 2 electrons. So now it has a charge of a negative 2. Okay. Bromine is in group 7. It's going to pick up 1 electron to give you the octet fulfillment. So it would be a negative 1. Nitrogen is in group 5. Okay, it's a nonmetal. It's going to gain electrons. Specifically, it's going to gain 3 of them. And then aluminum, being in group 3, and it's a metal, are going to lose electrons. And it's going to lose those 3 valence electrons to give you a +3. Okay, notice the name here for the nonmetals. Okay, this is sulfur. Now, when this becomes an ion, we change the name to sulfide. Okay, so this is now sulfide when it's the ion. Bromine, when it's in the element, is called bromine. When it picks up that electron, its new name is now called bromide. Okay, and nitrogen, when it becomes an ion, now is called nitride. The others, the metals, it just becomes lithium ion. That's it. Magnesium ion, aluminum ion. That just tells you that they are the ions if we don't change the parent name. So the nonmetals names change, and which is important because when we start naming these compounds, when they're combined, and you see sulfur and it's combined with something else, then we have to change the name from sulfur to sulfide. Oxygen becomes oxide. Okay. Earlier I said isoelectronic, meaning we had those examples where the ions had the electron configuration close or similar to a noble gas. That is the term isoelectronic. That is when they share the same electron configuration. They share actually the same number of electrons. Okay. For example, magnesium ion plus 2 lost 2 electrons. So now its new electron configuration is like neon. 1s2, 2s2, 2p6. So the magnesium ion is isoelectronic as neon. Iso meaning the same number of electrons. Okay. Phosphorus becomes phosphide. And now when it becomes phosphide is isoelectronic with argon. Okay. Take a look at these. We got the calcium ion. Okay. Calcium is in group 2. That means that normally calcium element would have had 4s2 at the end, but it's a metal, so it loses 2 electrons. So now its new configuration is given 1s2, 2s2, 2p6, 3s2, 3p6. Okay. And oxygen normally would be 2p4. Chlorine would be 3p5. And aluminum would have been 3s1, 3p1. Okay. The elements, but all of these became ions. So this is the new electron configuration of the ions. And the calcium ion is isoelectronic with argon. The oxide, which is from oxygen, is isoelectronic with neon. Chlorine became chloride, isoelectronic argon, and aluminum is isoelectronic with neon. Okay. Let's take a look at this here for a second. We're looking at some elements. Okay. If we look at the top, we see selenium, Se. And we got the mass number given to you as 78. Okay. The difference between the two is the selenium on the right side is a -2. It's an ion. Now, both of these have the same number of protons. We haven't done anything to them. Okay. Se is Se. So we would expect them to have the same number of protons. Aluminum is still aluminum. Okay, we're still working with aluminum 27. The difference between the two is this one here for selenium has a -2 charge, so it's an ion. What would change would be the number of electrons. Aluminum went from aluminum 0 to aluminum plus. It lost electrons. Okay, and so selenium would have 34 protons for the element or the ion. The number of electrons would be different, okay, because the ion picked up 2 electrons, so now we have 36. The neutrons for both are the same, okay, same amount. For aluminum has 13 protons, whether it is the element or whether it is the ion. It has 13 electrons when it's the element, but it lost 3 electrons when it's the ion. Now it has 10 electrons. And the number of neutrons, obviously, in this case, remains the same. Okay. So that, ladies and gentlemen, ends chapter 5. Okay, so make sure you work through the worksheets on this chapter that are on the website. And any questions right now? No? Okay, what I want to do is chapter, we're obviously not going to finish this, but we will knock it out tomorrow and get you ready for the next chapter's quiz coming up next week. Chapter 5 deals with the periodic table, okay? And it's pretty short, only about 25. Now, some of this information, I already introduced it to you, but we deal with the trends of the periodic table. Okay, this periodic table is pretty old. Well, not the modern one, but the idea of a periodic table goes all the way back to a gentleman scientist by a Russian scientist, Dmitry Mendeleev. He, back in 1869, arranged the known elements of the time into a table. Now, what's fascinating about this is the time period that, we didn't have all this fancy equipment. And so his deductions were based on observations and observing the elements and how they reacted. Couldn't really explain why they did that like we have it now. Right now, we introduced to you the groups, and what they all had in common was the fact that everybody in the same group has similar reactivity because they shared the same number of valence electrons, and therefore would have a similar type of reactivity. Okay, so this is his periodic table way back when. Later on, closer to modern times, there's Moseley. He arranged the periodic table with increasing atomic numbers. Now, let me back up for a second. Notice in Mendeleev's table, there's a lot of holes in it. And what that initiated was scientists to go look for elements because his table predicted that there was missing elements out there. And sure enough, as time went on, scientists were able to find the elements that were predicted by Mendeleev's table. This table here is kind of dated because if we look at down here, number 115, number 117, and 118, those have fairly recently, I believe about 2000, a couple of years ago, they were actually isolated. And so they were empty at one point in time, and they were able now to make them and verify. So our periodic table right now is full, 118, which you think about for a second, you can predict 119 based on what you see how the periodic table is working now. If you were the scientist working on finding the new element, where would you predict 119 element 119 to be? What energy level would it be? Right now we got 7. What would you predict it to be based on what you observed? Anybody want to take a wild guess? Don't need to guess. Just look at the trend. See how as you go across the periodic table, it wraps around and starts. Element number 119, which doesn't exist right now, but if you were the one looking for it and wanting to make it, exactly, Abigail, it would be an energy level the next one up. How many valence electrons do you think it would have? Exactly, because it would fall right under, it would fall under group 1 valence electron. So Whether there's people out there looking for 119, I'm sure they are. But the periodic table, hence periodic, is because there's a lot of periodicity, a lot of trend involved. You already know one trend. As we go down the periodic table, you can see the elements get bigger. Okay, so the size, the relative radius of the element gets bigger as you go down the periodic table. Okay. So anyway, Moseley arranged them in increasing atomic number. Okay. And then as our introduction to energy levels came into play, and we talked about the electron configuration of the electrons, and I say, hey, think about group 1 and 2. Think of those as the S elements, or we here in this case call them the S block. And then the ones from 3A to 8A, think of those as the P block. And then we got the D block and the F block. So it's amazing that Mendeleev came up with this way back when, and not knowing how the electrons were kind of put together at this point, but it was able to do quite a bit with limited tools that he had. All right, so the horizontal rows, I introduce them as energy levels, but we normally are called the periods, okay? So the vertical columns, you already know, we call them the groups, okay? And you might even hear the word family, simply because they have similar reactivity. Now we know they have similar reactivity because they have the same number of valence electrons, okay? So similar properties. Now we have two groups. We have the Roman numeral A group. Those are the main group elements. And then the ones inside the D block, they're called the B groups. Their alternative name is called transition metals. So we got the A's, which are the main group elements, and the B, which are known as transition metals. Okay. So period represents the shells or the energy level. So we got period 2 here across the board, period 5 in this example. And then we got the groups, group 1A, for example, and group 6A. Okay, they're called groups or families. The term family is also used quite a bit. Okay, but they also have their own little special name. So everybody in group A are called the alkali metals. Okay, the next group in, group 2A, they have their own little special name called the alkaline earth metals. Now the group 7, that's where you have bromine and chlorine and fluorine. They have their own little name too. They're called the halogens. You may be familiar with some of these. Some of you may have halogen lamps in your headlights, okay? And then the group 8, that's the last group on the periodic table. Those are called the noble gases. Again, noble because they're very unreactive, okay? Now the D block here denoted by green, they're the transition metals, okay? They're the group B elements. We can't do a lot of prediction here, okay? A lot of things kind of change. The only thing we can predict is that they're metals and they lose electrons. But some of them lose 2 electrons, some of them lose 1 electrons, depending on the condition. So there's not much of prediction. For example, copper, which is number 29, can lose 1 electron or 2 electrons. It can be a +1 or a +2. Iron, we're all familiar with iron, number 26, can lose 2 electrons or lose 3 electrons. Okay, so difficult to predict. The only ones we can predict 100% are the metals in group 1 and the metals in group 2. Okay, the metals in group 1 will always have 100% of the time a +1 charge. And the metals in group 2 will always have a +2 charge. Okay, that's something important to remember down the road. Now down in the gray, the horizontal group, they have their own special name. They're called the lanthanides. Like I mentioned, if you look at that down here at the bottom, let me see if I can mark that so you can see that here. This number 58 normally would obviously come right after 57 there, right? You see that? And then we got 90, which will come right after actinide, number 89. Well, I'm gonna see if I can find a periodic table that's been expanded. What's happened is these guys, starting with 58, they have their own special name. They call them the lanthanides. Starting at number 90, they're called the actinides. Normally they're in there in the periodic table, but that makes the periodic table kind of spread out. So they pluck them out and compress the periodic table. So keep that in mind, that 58, I denoted here by the arrow, and then 58 is down here, starts with the lanthanide series, okay? All right. And that's what we just talked about. The inner transition metals, okay? Those are the lanthanide series and the actinide series. These two periods under the gray one and the kind of orange color from my end. Okay, those are called inner transition period metals. The green ones are transition metals. The inner transition metals have their own little name, lanthanide and actinide. And all the elements up to about 93 and greater, all of them have been man-made. Okay, as far as we know, they don't occur naturally. And the way they make them is they actually combine elements, have particle accelerators, and cause them to come together and to form all the new elements that have been created. So we have made quite a bit of them. Okay. All right. So what do we got here? I got 11. This is what I'm going to do. It's getting close to 3, and I got a 3:30 doctor's appointment. Let me stop here on slide number 11, and then tomorrow we'll finish this chapter. It's fairly short, and then if you need to, we have time for questions. If not, don't forget I do have my office time on Friday if you have any questions. So far, I've only had one student, so I'm assuming everything is going okay. Okay, slide 11. So, any Abigail or Luia, do you have any questions or comments or anything? Everything going okay? We're keeping up with the homework and the activities, and not too much of a problem there. Okay. All right. Well, thank you, Abigail. Hopefully I'll see you guys tomorrow, and I'll mark my slide that we ended. We'll continue with that slide and finish the chapter up. Okay. All right. Thank you.